In the quest to unlock the power of fusion energy, every fleeting moment holds immense significance. A groundbreaking achievement by a Princeton-led consortium has introduced heat-ML, a sophisticated artificial intelligence algorithm capable of pinpointing magnetic shadows within the confines of a fusion reactor in mere milliseconds. This innovation accelerates the computational process essential for safeguarding the most thermally stressed components of a tokamak's exhaust system, pushing the boundaries of what's achievable in fusion science. This pioneering work, meticulously documented in the esteemed journal Fusion Engineering and Design, revolves around SPARC, a compact, high-field tokamak currently under construction by Commonwealth Fusion Systems. In collaboration with the Princeton Plasma Physics Laboratory and Oak Ridge National Laboratory, the researchers employed a neural network trained on outcomes from the Heat Flux Engineering Analysis Toolkit, HEAT, to assume control over the most time-consuming aspect of the workflow, calculating the geometric shadow mask. By doing so, they maintained precision while drastically reducing processing time, paving the way for accelerated design iterations and instantaneous adjustments in pursuit of net energy gain. The comprehensive study, accessible via the DOI 10.1016/J fusengdes.2025-11500, builds upon the ongoing partnership between PPPL and the U.S. Department of Energy. The significance of magnetic shadows. In the intricate environment of a tokamak, magnetic fields play a crucial role in confining a plasma at temperatures exceeding those found on the sun. These fields channel exhaust heat along their paths towards the diverter, a critical component designed to withstand extreme conditions. Should the heat inadvertently strike surfaces lacking protection, catastrophic damage can ensue, leading to melting or structural failure. Engineers meticulously craft the layout of components to ensure that upstream tiles shield downstream edges, creating areas shielded by magnetic forces. As tokamaks such as SPARC push the envelope in power and plasma configuration exploration, the ability to rapidly update these protective maps becomes indispensable. For a beginner-friendly explanation of how a tokamak functions, refer to the Department of Energy's insightful guide, Transitioning from Heat to heat-ML Heat, the open-source Heat Flux Engineering Analysis Toolkit, employs a methodical approach to trace magnetic field lines and identify intersections with detailed CAD geometry, resulting in a shadow mask, a binary representation distinguishing shielded and exposed points. This collision detection process consumes heat-ML. On the other hand, leverages a neural network to directly predict the shadow mass from a concise set of equilibrium parameters, leaving the downstream physics calculations untouched. Initially focusing on a 15-tile segment of SPARC's diverter, where heat loads reach their peak intensity, this methodology promises a significant leap forward. The learning process of the model to equip the neural network with the necessary knowledge. The research team synthesized approximately 1,000 heat scenarios tailored to SPARC, encompassing a broad spectrum of plasma equilibria. The inputs fed into the neural network included parameters such as plasma current, the edge safety factor Q95, and the incident field angles at the upper and lower boundaries of the diverter carrier. By leveraging GPU acceleration, the optimization phase was condensed from minutes to mere seconds, facilitating rapid experimentation. When applied to previously unseen cases, heat-ML demonstrated remarkable accuracy in reproducing shadow masks, enabling heat to compute heat flux profiles with negligible discrepancies from the conventional pipeline, albeit at a fraction of the time. Essential insights: the capability to generate shadow masks in milliseconds paves the way for near real-time heat mapping on fixed diverter geometries. The precision achieved rivals that of Heat's established collision detection technique, while slashing the per-case runtime to mere seconds. primarily due to input-output time. Integrated as an optional module within Heat, engineers retain access to comprehensive CAD and physics contexts. Facilitates between-shot decision-making in the present, with potential to enable closed-loop diverter protection in the future. Constraints and future directions. Given that the current model is anchored to a specific mesh, applying it to a novel geometry necessitates the creation of a fresh heat dataset. The research team is actively pursuing strategies to broaden the applicability to other plasma-facing components and is developing mesh-adaptive methodologies. They acknowledge that collision detection remains a significant obstacle, even in axisymmetric scenarios, hinting at opportunities for surrogates capable of handling field line integration. In the grand scheme, merging heat ML with infrared diagnostics and a plasma control system could furnish operators with live heat maps that refresh instantaneously in response to alterations in shape, currents, or power during operation. Insights from the research team: by leveraging an existing codebase and integrating an AI surrogate, we've expedited the process of deriving valuable insights, opening up exciting avenues in terms of control and scenario planning, shared Michael Churchill from the Princeton Plasma Physics Laboratory. Implications for fusion science. High-field, compact tokamaks strive for exceptional performance in confined spaces. But their success hinges on managing heat within the operational limits of the hardware. The advent of faster, accurate shadow mapping empowers teams to evaluate tile designs, select optimal operating points, and circumvent vulnerable areas without enduring lengthy simulations. This transition propels operations from tentative trial and error to assured, data-driven control. If operators could visualize, in real time,